To start our discussion about performance and profiling, I'm going to quote Donald Knuth. The real problem is that programmers have spent far too much time worrying about efficiency in the wrong places and at the wrong times. Premature optimization is the root of all evil, or at least most of it, in programming. The key here is about optimizing for efficiency in the wrong places and at the wrong times. When we talk about optimization, we need to ask, what is performing slowly? We don't want to begin to optimize everywhere. And implicitly, what we're saying is we need an analysis of our software, right? If we need to understand what is performing slowly before we can begin to optimize it, then we need an analysis of the software to know where it's running slowly, right? This is referred to as profiling. Once we know where our application is being slowed down, we have to ask the question, well, which of these bottlenecks actually affect the user experience or the business bottom line, depending on what your application is doing and how it all works. Once you know which of these issues is relevant, you then have to ask, well, can we actually improve this bottleneck in a reasonable amount of time? In some cases, it's simply a question of looking at whether that amount of time is going to be worth it. Maybe you have an endpoint that takes too long, but it's going to take months for a developer to actually make it run quickly, and that endpoint simply isn't used enough for that developer to spend that amount of time on it. On the other hand, sometimes in computer science, you have problems that you cannot speed up. Right? Algorithmically, you are simply limited to a certain amount of time you are going to take on this problem, and no amount of performance optimization is going to change that. So at that point, it's just not worth spending your time on it unless you radically change your algorithm and find a heuristic or something. So those are the questions you need to ask before you even begin to optimize. Now, in production, you need to think about performance as holistic, right? You need a holistic analysis of what's going on. And for a web application, that means looking at not only the back end, but also the front end, right? When a user comes on and asks for a specific server, they're going to issue an HTTP request, and the server is going to come back with a response. And in that response is going to be HTTP, CSS, JavaScript, and that is going to affect the user experience. That has an impact on performance. Questions on the front end should include things like, how much data are we actually sending in each response? Whether it's in terms of images or in terms of code, what is the size, how many requests, how many responses are we sending back for a single request? How much processing time does the JavaScript take, right? These things are not equal. You might be sending a little bit of CSS, a little bit of JavaScript, and images that are the same size as the JavaScript, but the JavaScript has a greater impact because the browser has to not display it like an image, right? The data comes in, it paints it, and that's pretty quick. It has to take this JavaScript code, and it is then going to go through and parse the entire thing to figure out what it needs to do with it, and then run that code. So the impact is far greater. This class is about back-end web development though, and we are going to be focused specifically on performance optimization within Django. So we expect that we're going to have a Django website where we will have programmed views, URL paths, models, templates, and where we will have a database with our state data within it. When we load Django, the dispatch system comes online, the template system comes online, and that way, when the user sends an HTTP request, it comes through dispatch, which has loaded the URL paths, matches one of the URL paths so that it can send the request to one of our views. Once it finds that view, we can do whatever it is that we need to do, right? We can go ahead and we can load data from the database via a model, or several, mind you. We can reach out to the template system and have it load our templates. At some point, though, we have to come back and we have to return an HTTP response all the way back to our user. This is the core of Django. This is what we're going to be doing on virtually anything that we are doing inside of Django, even if it is supplemented by something like the Django REST framework. So yes, we might have view sets, we might have routers, maybe we're passing data through serializers, but this is more or less what this looks like when you are operating within Django. Now the good news is that when you're operating within Django, most of the performance bottlenecks are not within Django, right? Most of the work that we're doing is CPU bound, and that moves pretty quickly. No, most of the problems are when we have to reach out to external systems, right? When we have to make calls to the network or calls to disk. So the central problem is when we receive like an HTTP request, an HTTP response, there's a certain amount of time that we are waiting as the network gets us that data back. Similarly with templates, simply because we're reaching out to disk and disk access is slower than memory, just by virtue of how the machinery works within a computer, we know we're going to be waiting for longer if our templates exist on disk. And the database, well, the database could exist on a local disk, or it could be a network access that then has to talk to a local disk. So that one can be particularly slow. So we might say, okay, well, we know that at the fringe of access outside of Django, we have to somehow speed that up. So what are we going to do? Well, we're going to store everything that we possibly can within memory. We store computation in memory. We can store our templates in memory. And when I say we store computation in memory, I mean we pre-compute values, or we store things that, values that we have computed into memory. So we can then begin to remember or cache all of this data, whether it's pre-computed or something that we've pulled off of templates or from the database. And this way we can limit the number of times that we have to access templates from the disk or access data in the database, regardless of where that database exists. Now for small sites, that will work just fine. However, for large sites, that's going to be a real problem. You may remember that from an infrastructure standpoint, Django is going to exist on multiple computers. When requests come in, they generally go through a load balancer, and that load balancer then distributes the requests out to the various machines that are running Django, and those machines then reach out to a single database for state. So that's a little bit of a problem, because if we have all of our various pre-computations within memory on any one of these computers, yeah, we might be saving a little bit of time on a single one of these computers, but what if one of the other requests that could benefit from that cache now exists on a different computer, is received from a different computer? We haven't optimized anything. We haven't saved ourselves from doing that computation in that scenario. So as we think about the load balancer, the stateless logic, and the state, we have to first say, okay, well, where can we speed up access to state? So internally, instead of having each computer store pre-computed values in their local memory, we can use a cache at the infrastructure level to store that information. In this first instance, we can see how this helps speed up access to the database, right? We have a request that comes in through the load balancer to this computer, and we start by saying, oh, well, have we already asked the database for this? Have we already computed whatever database query this is? And if yes, well, then we can just return a response. If no, then of course we reach out to the database, we get that data, we do the computation, and then we should send that data back to the cache so that in the event any of the other computers have to do this computation, well, they just ask the cache. Now, in a second instance, we can add a cache all the way at the front. This way, we can, whenever a request comes through, if it's already been pre-computed, it just responds directly back to the user. Now, of course, if the request comes all the way through, we can then do the cache internally according to the database, store it in the cache if we need to, and then return that response, which will then end up in the very front-facing cache in the event that it has the right headers, it's talking to the same user, all of that. So it gets a little bit tricky. Caching is not quite as simple as I'm painting the picture here, but it does radically speed us up because we avoid having to do all sorts of work. To review, each and every single application needs to be analyzed before any performance optimization. As I don't know your application, I can't comment on what is going to be needed on your site, on your application. However, there are a set of well-known problems that web developers see all the time, and for which Django provides a few solutions for. So the first thing that we're going to have to talk about is optimizing I/O, right? We already talked about the fact that reaching out to the disk, reaching out over the network takes extra time just because that's what we're doing. It just takes more time than sitting on your CPU. So we have to optimize I/O, and the first thing that we want to do is we want to limit the number of times we get data from the database. So we want to do some query optimization, and then we can limit how much data we get from the database. Now, if we can, optimizing I/O is good, but if we can avoid doing the work at all, we want to do that, right? So we want to talk about caching data. Now this involves, as I've mentioned, changes to infrastructure and changes to the way we think about the very logic of our entire application. So this is not a small set of changes, and it gets very, very tricky. For instance, we have to ask the question, how do we invalidate stale cache data? If someone sends a request to that front-facing cache, but the data on the database has changed because of a different request, we're now showing that person the wrong data. Is that okay for our application? For some websites, that's going to be fine, but for some other websites, that is absolutely not okay. And so we have to figure out, well, how do we then tell the cache, oh no, this data is no longer valid? So some people will talk about cache invalidation according to time, but in a lot of circumstances, you may have to do cache invalidation according to the data that is coming through, and that is hard. It's very tricky. So in the next few videos, we will begin to touch upon this, right? There's a whole world there. We could do an entire class on just performance optimization, and we're just going to talk about these sort of two fundamental problems and the various solutions that Django gives us in the next few videos.